So if you can kindly take a seat, we can start this first session on grids. We will have 3 presentations today about activities in ongoing grid projects at national and international levels. So the first speaker, let me introduce the first speaker. The first speaker will be Ralf Niederberger from John von Neumann Institute for Computing of Research Center in Jülich. And his main interests are high-speed communication, internet security, and is currently the leader of the service activity, network operation and support of the DESA grid project. He will talk us about the DESA project, network operation and support. First experiences. Please.
Hello everybody, can you hear me? Can you hear me? Yes? Better now? It's better now? Okay. Hello everybody, I welcome you to my presentation to the DESA project network operation and support first experiences presentation. I will divide my presentation in several parts. First I want to introduce the DESA project as a whole. In the second part I will show you the applications and the network requirements which will be seen in the DESA project. The third part, I will show you the network infrastructure, how it is structured, who communicates with whom, and so on. And I will round up with future network challenges and with a summary. So what is the DESA project, its missions, its goals, and so on? The DESA project is a consortium of 8 leading national supercomputer centers in Europe. Where are IDRIS, Research Center Jülich, CINICA in Italy, EPCC in UK, CSC in Finland, Research Center Garching in Germany, SARA in Netherlands, and the European Center for Medium Weather Forecast in UK. It's a EU-sponsored project, and it's originally was granted for a 5 years period. We changed it to 4 years since we included 3 additional partners, the Barcelona Supercomputing Center, the Research Center in Stuttgart, and the Leibniz Research Center in Munich. And additional partners as associated partners will follow in the next time from different countries. So what is the mission and the objectives of the project? We want to contribute to a significant enhancement of capabilities and capacities of high-performance computing in Europe. We want to do this by including many supercomputers, putting them together into a joint infrastructure, and deploying and operate a distributed multi-terascale European computing platform. We want to build a European virtual supercomputer made of this individual supercomputers. We want to contribute to the deployment of an extended heterogeneous grid computing environment for HPC in Europe, and we do this by including this virtual supercomputer in the global grid environment in Europe and the world. We interface the DESA research infrastructure to the European IT infrastructure. The strategic vision of the project is to deeply integrate and tightly couple supercomputers, computational resources, and not use a loose federation model as it is in grid environments. You connect computers and virtualization facilities, but it's not tightly coupled. We want to do it tightly coupled, and I will show you later on how this will be done. And the vision is to enable new science. That's the only criteria for success of the DESA project. if we can say we have enabled new science after the 4 years, we haven't reached our goals. The IT systems integrated were first of all IBM supercomputers, but we are not drawn to this systems. We can introduce every kind of supercomputer system, and the supercomputers we used were chosen only from the operational model of the supercomputer centers. They decided when they needed a new supercomputer which is the best, which fits best for our operation, and most of them choose to use an IBM supercomputer, but that was only at the time where they choose to introduce a new supercomputer model. And we want to become heterogeneous. That means we want to have other systems also included in our European supercomputer system. DISA's vision is to integrate high-end computing systems. We want to promote cluster software to distributed supercluster middleware. We have global file systems, we have batch managers, and we want to develop them to distributed global file systems and to multi-cluster batch managers. Batch managers which include all these systems and where we can route jobs from one system to another system. The project organization is very simple. We have networking activities. That's normal with EU project management and dissemination. You need this. Then we have service activities that are activities which are related to a special service. There's no research. It will be done for the project. And we have here 5 service activities. It's network deployment and operation, global file system, middleware, applications and user support, and the whole bunch of security. The blue institutions on the right show you who is responsible for this special kind of activity. Additionally, we have joint research activities. We provide the applications with support, and we want to have early adopters of this technology. We show them how to use the supercomputers, how to use a virtual supercomputer, European supercomputer, and we do this for many kinds of science. It's for material science, cosmology, plasma physics, life science, and also industrial applications. We also have a joint research activity for coupled applications, and the joint research activity 7 deals with heterogeneous resource management. Means, for example, how can I access the different resources, do it by Unicore, middleware, or Globus, or however. So, how is a data facility, how can it be seen? We have many supercomputers with their own operating system, with their own disks, and these are put together via a wide area network. Currently, this is the red line is 1 gigabit per second network across Europe, and the ring tells you. One moment. This ring here tells you that the single system image we are creating. These are the different supercomputers with its disks, and here is a wide area network provided by GEANT, Renator, DFN, and GAR. It's the European part and the country part. We started with 4 supercomputer sites. Then it has been Idris in France, Jülich in Germany, Garching in Germany, and Cinica in Italy. And we will go in the next phase with other systems. This single system image will be connected via normal connections to other systems in the grid environment. This, for example, it could be a university somewhere in the world, and this research center in another country, and so on. They connect to this single system image via SSH or via the services we provide to connect to the system. These will be the extended grid services, portals, web-like services, interfacing the core platform to other virtual organizations. So we can see the whole environment in 3 circles. It's first the single system image with the IBM supercomputers, additional heterogeneous systems within the DISA internal grid, for example, Zara, an SGI system, or Barcelona, it's also an IBM computer, but a Linux, not an AIX system. And these are also connected to this internal network, giving an internal grid. And here is what I mentioned earlier, the connection from outside world. We provide this system to the outside world to enable new science. So this is only a sketch of the DISA facility. We started, as I said, with 4 institutions, having 4,000 processors, 5 to 8 gigaflops per processor, making about 24 teraflop aggregated peak performance, with 125 cabinets spread over Germany. The left one, for example, is a supercomputer system in Jülich. So that you can see it's a hall where you can play football or volleyball or something like this. It's a great hall. The phase 1 network has been implemented in August last year, and we are currently in the phase 2 integrating heterogeneous systems. SARA, SGI system, has already been connected. ECMWF will be connected in the next 2 or 3 months, and also CSC in Finland will be connected this or next month. We will get also a phase 2 in the network environment, higher net bandwidth, 10 gigabit or more. And we are just discussing this with the INFN and GEANT, how we can manage this. We are dependent on these infrastructures. With the current infrastructure, we can get 10 gigabit to each of these sites. So what are the applications and what are the network requirements? DISA provides an integrated supercomputing environment with efficient data sharing through high-performance global file systems, highly transparent to end users. The user doesn't know where his file resides. He starts a job, brings it into a queue, and it can be computed somewhere on any of the systems. And the files will be accessed independent where the job is running. It's not that the file will be transferred to the system where the job is running. The job will access when the job is. The file will be accessed when the job is running. It's a global parallel file system. The user doesn't know where the file really is. DISA enables job migration across sites. It's also transparent. The user submits the job into the local queue, and the virtual supercomputer decides where this job should be run. We transfer it to another system where it better fits into the job queue, and there it will be run. Applications demanding huge resources can be run as such. They have not to be modified to run on this virtual supercomputer. Also, good applications which are distributed by design can be executed. For example, the old term meta-computing, which everyone says it doesn't work across wide area networks. This can be used here, and if you have an application which really makes sense to do it as a meta-computing environment, you can run it here. The operational model of the DISA supercluster is similar to a true monolithic European supercomputer. It doesn't matter if it's on one location or if it's divided. The main difference comes from the coexistence of several independent administrative domains, and there we have to deal with how to administrate the single systems, how we share information about new users, and so on. So what are the network requirements? As you know, we heard it yesterday, bandwidth on demand services and pre-allocation bandwidth services are not available currently, at least not in a wide area network. And so we decided to have a dedicated network interconnect between the supercomputers. It allows unconstrained and undisturbed use of predefined communication bandwidths. And that is required to evaluate interaction between involved supercomputer systems, between the applications and also the network. With a dedicated network, we can really see, is it a problem of the network, is it a problem of the system? We don't have to interfere with other traffic classes. It allows to locate bottlenecks within the offered services as well as within communication environments because of the reproducibility. So since dedicated interconnects are very expensive, we talked to GEANT and the INFN, and we decided to have a virtual dedicated interconnect. We realize it by premium IP service. It's similar to that of virtual leased lines. Data packets using premium IP will experience no congestion regardless of load of other traffic classes. As a result, delay and packet loss are kept to a minimum. And what you get from the GEANT's premium IP service is upper bounded one-way delay, upper bounded instantaneous packet delay variation, no packet loss due to congestion, and a guaranteed capacity. Premium IP says that the provider only gives 10% of his capacity for premium IP services. So he can guarantee that this service level agreements can be handled. So currently we have no statements concerning delay and jitter. The applications haven't said what they really need. And we think with a global parallel file system, it doesn't matter if we have some delay, if we have some jitter. The global parallel file system doesn't take care of this. In general, delay and jitter depends on hardware used within the network, which switches and routers you're using, how long are the distances between systems, and so on. It depends on the design of the infrastructure. If you have direct connections, or you need to go another way or something like this, and it depends on the real application. Nevertheless, minimum jitter and delay is indispensable, especially if you have high bandwidths you need to use. So we started, as I already said, with a 1 gigabit dedicated network infrastructure. We have already connected 5 sites. CSC will come soon, and as I already said, ECMWF will already be integrated within 2 months. Current round trip times are about 13 to 20 milliseconds because of the premium IP service. I told you that only 10% of a line may be used for premium IP, so we had some links to get longer, not the direct link, and there are some links which may be 60 milliseconds or something like this. We plan to connect our infrastructure to the TerraGrid, which is a quite similar project in the US, and there we expect to have 170 milliseconds. We have to deal with this with our applications. These values cannot be reduced because of the speed of light. You know, transferring on fiber is about 2/3 of the speed of light. Redefining system network parameters is needed because of the so-called bandwidth delay product. It's the number of milliseconds multiplied by the bandwidth, and so you have, for example, 20 megabit bandwidth delay product, which means, for example, you have to set the TCP send and receive space, in this special case to 2.5 megabyte, and that's not the default values. Other parameters had also to be redefined. You can see it in the report, which is on the website. There are all parameters we changed specified. We tried to use this connectivity between the supercomputers with an iPerf program, which you can use in the UDP or TCP fashion. And we took 10-second data streams side to side, and we got 930 megabit per second from the 1 gigabit line. That's, I think, is very good. This is, of course, a special program. It's tuned for network tests, and a real application, for example, FTP or SSH, doesn't get this throughput. But you get it if you have many connections in parallel. Dependent on system, network options, CPU usage, system configuration, network layout, local and remote network configurations, this throughput may vary. The global parallel file system we use can give, without any problems, 10 gigabit per second within the system, and we already tried it via the 1 gigabit line, and it fills this 1 gigabit line up also without any problems. It depends on the local configuration. If you have multiple servers and multiple clients using this connection, you can fill up, for example, a 30 gigabit line. TerraGrid has shown this in 2004, that it's doable. And we want in the second phase of our program, of our project, use 10 gigabit lines, maybe at 1 or 2 locations a little bit more. We will see how much we really need. I'm too fast with my fingers. Some comments about security. We decided to have a net of trust. We have here the supercomputer, which is connected through the normal connection via the local network. Here's a firewall, and for example, if you have some university which has nothing to do with DISA and wants to connect to the supercomputer, it uses this way to this node. If someone wants to connect to this node from the DISA side, it uses this connection, and as you see, it's within the normal NRAN and GEANT communication. Currently, because of the premium IP service, we use the normal lines, and we decided to solve this security problem using here router access lists, specifying that only DISA sites may use this this part of the network. So we defined a net of trust. We had to negotiate security policies, and we defined a DISA third team. If someone has a security problem, he informs the other sides about the security problem. Users on supercomputers are well defined, so we could say if someone has access to one supercomputer, he has also access to the other supercomputer. We know him. The model which I showed you implies alias IP addresses for interfaces to know to which connection to use. And it needs extended routing configuration. So what is the network phase 2? We want to connect all systems with 10 gigabit per second, and I think it will be a star-like network with a router somewhere within the GEANT infrastructure, having wavelengths from the site, from the supercomputer, directly to this router, so that we have a star design of the network. So what are the future network challenges? A new network layout using GEANT2 and the NRAN's infrastructure. I said star-like, using point-to-point light passes. We have to redefine system parameters, and again, the bandwidth delay product says we would have to have TCP send and receive buffers with 25 megabyte. That's very much, and you can't use this for local communications. So, but that's not a problem, because the global parallel files we are using uses parallel streams, and so it's many TCP sessions you are using for one file transfer, and so you don't need this 25 megabyte TCP send and receive space. Security considerations also there are some challenges. Future bandwidth on demand protocols, superfluous dedicated communication lines. So we have the normal site connect also with this DISA traffic. The net of trust concept doesn't fit anymore, and so we have to think about new security models, high-speed firewalls, load balancing firewalls, dynamic firewall protocols having the problem that grids always use unknown ports to communicate, and so we have to think about dynamic firewalls which open special ports for only the moment of the application's traffic. The same considerations come up if you connect the internal grid to the external grid, to the European grid. You have to deal with firewalls, and you have to think how you can do it. And also users on remote sites are no more well defined. So to come to a summary, DISA adopts grid technologies to integrate national supercomputing infrastructures and operate as a virtual European supercomputing center. The big challenge ahead is to demonstrate the relevance of this strategy for the production of first-class computational science within Europe. DISA does not solve all the problems in grid computing, but rather tries to provide the most efficient solutions to some of them. And interfacing this core infrastructure, this single system image, to other infrastructure is a fundamental priority for DISA. So we think that we get important synergies especially in the application area. So the real vision of DISA is using grid technologies to integrate and interface IT systems, that this is the way to go to create a new research infrastructure and a new research dimension in Europe. Prerequisite to all these DISA challenges is the existence of a high-speed, error-free multi-protocol network. Thank you.
Thank you very much, Rolf. The floor is now open for comments or questions. Actually, I got two questions myself. The first one is, if you allow cluster computers, I mean new clusters, new high-speed clusters, do you foresee any limitation in the number of GPFS clients that you can connect?
We have to see this. The software is just in development. IBM has currently a version for IBM systems and Linux, because they also provide Linux, but they said they want to give the software free for others to adopt it on other systems, and then we see how much clients can be used. We know that we could get problems with the Barcelona supercomputing center, which have 4,000 processors, which are every processor is its own client. And we have to see how it fits.
Okay. And the second question is, I mean, having this very nice network connection, do you will allow geographic parallel computing? I mean, geographic MPI or something like that, or your applications don't require this kind of?
As I said, we allow grid applications which are distributed by design and which use whatever communication facility they can use it. It depends on. Currently, we have the net of trust. You can use every port, but if we have in a second or third phase this firewall issues, we have to see if we can allow all possible communication possibilities.
Thank you very much. Are there any other questions from the audience? Yeah. Yeah. Please use the mic.
Sorry. My name is Walter van Dijk. I work for ServNet, and I've got a question relating to the last things you said in response to your question. It's about the concept of firewalls. Why would you need firewalls in this concept? If you're going to work with light paths on a point-to-point basis, would you be needing a firewall?
We need a firewall if you connect from extended systems, which are not belonging to the DISA infrastructure. For example, if the University of Chicago wants to connect to a supercomputer, and they want to visualize data or want to transfer a big data set to be worked on via a job. Then you need the transfer from the university to the DISA supercomputing system. And there is a place where firewalls come into discussion. Within the real infrastructure and with the light passes, you don't need it. That's right. Okay. Maybe you need it to allow, I'm thinking not of real dedicated light passes. I think in 1 or 2 or 3 years, you can say, I need for 1 hour, for 10 seconds, a light path from A to B. And then someone has to decide, is this allowed to give this light path away for this application? And then there must be some instance who says, yes, that's allowed. And then you need something like a firewall. It doesn't really look into the packets. It says, as it's for IPsec connections, it says this connection is allowed, and then it doesn't care about the connection.
Okay, thank you.
Another question?
It relates to the it relates just a comment to the security issues. I think what you need if we look ahead for some years and you get a switch network, what you need is a sort of authorization and authentication for this resource.
Yes.
I don't think you need a firewall then.
I name it firewall. It's a management. It's a security management station or place. I use firewall not as a black box as it sometimes it's used. I remember the first definition of a firewall. It's the implementation of a security policy. It's more than only the black box.
Okay, thank you. So if there are no more questions, let's thank the speaker again. And let me introduce the second speaker, which is Ariel Alexiak from Application Department of the Poznan Supercomputing Center. I mean, his research interests are in the field of scheduling and resource management in grids, and is being actively involved in grid projects like GridStart, GridLab, SeaGrid, and ClusterX. And he will talk us about the single point of access to resources for HPC Europa. Please.
Welcome. Okay. Can you hear me? No? Is it okay right now? Yeah. Okay. Okay, so thank you for introduction. Actually, I'd like to present a talk together with Bartek Lewandowski about unified access to grid infrastructure. So we decided to modify a bit the title, and there are two authors because we would like to present results of two projects. HPC Europa, which is still running project of 6th framework program of European Union, and GridLab project, which is already ended, and it was the project from 5th framework program. And in particular, we would like to focus on the activity called single point of access of HPC Europa, and then GridLab mobile services. Okay, so maybe first I should mention that this talk is more about access to infrastructures, more about the higher level access to higher level services and so on. Not so it doesn't touch the underlying network so much. So I have to talk about it. Okay, so the outline is the following. So we start from some introduction and then explain, say a few words about the GridSphere portal framework, which is used in two cases in HPC Europa, single point of access, and then by mobile services in GridLab. And then we describe these two approaches, so the single point of access of HPC Europa and the GridLab mobile services, and we'll end with some conclusions and next steps foreseen. Okay, so maybe I should give some motivation why we like to talk about this mobile services and the single point of access together and so on. So I think you are familiar with grids, but okay, so we can say that the grids provide environment for collaboration and some advanced computations, but what users require? Users probably require to access these services in transparent and easy way. Despite this resources and the grid services can be very heterogeneous in terms of, for example, different machines, different services providing particular functionalities, and also different devices from which user try to access the grid. Okay, so we can summarize it in the following way, that users want to access various diverse grids and HPC facilities, regardless of user's location. We can call it an idea of anytime, anywhere access, using diverse mobile devices. And he wants to do it everything in a transparent and easy way, not to without knowledge about underlying complexity and heterogeneity. So the conclusion is that they need some kind of uniform access to this heterogeneous resources, and some methods for mobile access from different devices from different locations. So that's why we like to present approaches for both problems, let's say, which are closely related. So the access to heterogeneous resources and access using mobile devices. Okay, so this illustrates this diagram. So you can see here. So at the bottom, it's the access from the single point of access. You can this is the interface to underlying grid services like Globus, Unicore, and some, for example, resource brokers and so on. They have they provide let's say similar functionality, for example, submitting a job to the grid, but in a different way using different interfaces. So we need something which unifies these interfaces and provide it in a transparent, unified way to the user. On the other hand, you can see here on the top that users can access this functionality using different devices, ways, and so on. For example, using command line client even, or some TIC client, some standalone applications running on the user's machine, or by portal, or even mobile devices. And basically this lower layer is something that HPC Europa and the single point of access activity is working on. And the top level is more that GridLab mobile services were working on, actually, in particular mobile devices access. Okay, so after this short introduction, I think maybe okay, so I should mention that this single point of access in both cases is based on the GridSphere portal framework, which was developed in the scope of GridLab project. So I think I should say a few words about it. So this GridSphere portal framework is open source, and it's a portlet-based web portal, and it provides many possibilities to customize this portal. For example, to set some themes for particular users, to group portlets in projects, and so on. Thanks to using portlets, user and developers can easily plug particular functionalities into the portal, and if they are written using standards, they can be easily portable to other containers and so on. And this is an interesting concept of separating presentation layer and business logic in using portlet services. And finally, there is a Grid Portals web application which supports access to grid services. Okay, so I start now talking about HPC Europa activities, especially about single point of access. So let me say a few words about the project in general. So the whole name of the project is Pan-European Research Infrastructure on High Performance Computing for the Science of 21st Century. But shortly, it should provide access to HPC resources and services for researchers in Europe, and that's the main goal. And this is a quite large project. You can see 14 partners across Europe, and among them there are 6 centers that provide so-called transnational access program, which enables users from other centers, other parts of Europe, to apply for grants to European Commission and then use these resources. So if you compare, for example, with DESA project, which was described before, I think that the whole HPC Europa project is more about providing this access to researchers, and so including some procedures, grants, some training, supporting tools, and so on. Then to building this, let's say, monolithic European supercomputer. And HPC Europa, besides the transnational access program, also contains, let's say, a few smaller activities, and one of them is the joint research activity number 2, which is a single point of access. So the responsibility of the single point of access is to build a portal to these resources of HPC Europa. So this main motivation is to provide a uniform access to resources of all centers, transparent and regardless of user physical location. So we want to build a portal which enables user in an easy way to access these resources, to improve resources availability and utilization. But the assumption here and requirement is to keep local autonomy of the centers. I mean that to allow centers to use their own middleware, with middleware interfaces and so on. So that's something that make our life more difficult. I mean, life of developers of this project. But that's the assumption. And the very important issue here is also the existing. The need for accounting system for the whole HPC Europa. Okay, so if you look at this picture, I think it illustrates the situation. Let's say so. These are 6 centers which participate in this single point of access activity, and you can see here these blue boxes are grid middleware So for example, GRMS is a grid resource management system developed by TNC, which provides functionality to submit jobs, monitor them, and so on, to find best resources. But other centers have their own systems, like Univ or GEANT and so on. Additionally, this is based on different local resource management system, queuing system like Load Leveler from IBM or SunGrid Engine and so on. So you can see that this environment is really heterogeneous. And just there are some details about it. Maybe I will not go into details, but you can see here how different are these services. So. Okay, next very important part of the single point of access is accounting system. This accounting idea in the Europa is based on the allocation unit concept, which means 1 teraflop sustained for 1 hour. So using so the number of allocation units is a number of teraflops used by a particular number of hours, and these teraflops are measured using Limpag benchmark, which is de facto standard in this area. For example, I think the machines in the list, top 500 lists are measured in this way. And so the idea is to keep these records of allocation units and use them for two purposes. First, to charge the European Commission for the user resources, because for every machine, this allocation unit is let's say corresponds to some amount of euro. So then, for example, after some period of time, centers has to charge European Commission for the use of resources. And next need is to limit the maximum amount of used resources. And so currently, there are many local accounting systems and accounting approaches in centers of HPC Europa, and what we want to do is to provide a global accounting, so provide a global pool of allocation units which can be used by users. Okay, so these are some more details about this accounting. So basically, there are different ways of gathering this data from central databases to even some manual copying data from logs of local systems into Excel files and so on. Anyway, there are some interesting ideas in this local centers. For example, there are concept of project and budget, which means that for each machine or each HPC center, HPC system, let's say, there are several projects can be allocated, and for each project can be several budgets can be allocated, and then users can be assigned, let's say, to particular budgets. And then if the user submits a job, he has to specify which budget should be used for this job. Okay, so what are we doing now is the development of the single point of access portal, which should cope with this problem of heterogeneity of underlying resources and so on. So you can see at this diagram that we are going to develop some, let's say, uniform or generic interfaces, for example, for job submission, job monitoring, and so on, which are based on the functionality of existing systems and maybe on some standards where possible. So maybe I will describe it on the basis of job submission interface. So if user wants to submit a job, he uses job submission portlet, which generates the job description in a standard way. We use the job specification description language, which was designed by in the scope of Global Git Forum, and then through job submission service, it is passed to the appropriate plugin, which is then dynamically loaded. For example, if user selects, for example, business supercomputing site, then it dynamically loads this GRMS plugin for the resource management system, which is deployed here, and then this is translated into the native, let's say, native job description language for this resource broker and submitted. So that's the general idea, and what we want to do is to do it for other functionalities as well. And then the nice feature is that these plugins in turn the description of functionality they provide. So these portlets, also they are based on some general uniform interface. They can adapt this interfaces, this layout to the functionality. For example, disable some fields or and so on. I will show you some examples later on. Okay, so a few words about the submission interface. So as I've mentioned, we based it on this GGF JSDL specification, which is still evolving, but I think that it's a good approach to try to use any standards that are available or some de facto standards and so on. And you can see that this is example of this is a general schema of this job description, which consists of these several parts, like a description of application, resources, and so on. So application looks as follows. The largest part is the specification of resource requirements, like memory and so on. There is also network bandwidth here. Okay, so an example of plugin. So, for example, for GRMS, the following basic functionality is provided right now. So you can submit jobs to the features and so on. And this transformation from this standard job description into this specific one is done using in the GRMS plugin using the HSL style sheet, which means that we don't need to change the source code. We just can change the description, this XML for transformation, and we can change some interface and so on without need to restart the portal. So that's the example implementation. Okay, and here you can see some examples. So you can see here some part of portlet for job submission, a very simple one. But what I want to show you that if, for example, this is the general interface, part of the general interface. If you want, for example, to submit job to PSNC, and you select the appropriate site, then this portlet just to adapt to this functionality, and you can see that the basic layout location of some fields and so on is similar, but some of them were disabled or some list of values were limited. So for example, this is for resource requirements specification, and for GRMS you can see that the list is shorter and so on, and some operations are here, for example, are limited to the equal to and so on. So that's just example. Okay, I think it's time for some status of this activity. And as I said, we designed the uniform job submission interface, and now we can easily through the same interface, using the same portlet, we can submit jobs to 6 centers in the HPC Europa using 5 different resource brokers, and our portlets are based on the JSR 168 standard, so we can port these portlets into other container as well. And next steps are, of course, development of the remaining interfaces, but also the testing interoperability of authentication models, because I didn't mention it here because there is no time for it, but there are many problems with security issues concerning this heterogeneous problem of heterogeneous resources, because there are different security models. But okay, so and next step is also the development of application-specific interfaces, because some more complex applications require specific portlets for them, and the global accounting, as I said. And we can. So this is, I described this lower, let's say, layer of this picture that I showed at the beginning. So trying to build an uniform interface for heterogeneous resources. And now Bartek will say a few words about access from different heterogeneous devices to this interface, to these resources, which were developed in the scope of the lab project.
Okay. So now I wanted to tell you something about GridLab project and our approach. Approach to meet requirements of mobile users in our project, mobile users of grid services, grid applications. Shortly, GridLab project. This project is already, as Ariel mentioned before, this project just finished this year in March. The main goal was to develop grid application toolkit and several grid services and test it in real testbed environments. And during this short presentation, I would like to tell you something about mobile services in context of grid environments. At the beginning of the project, we had to ask mobile users what are their requirements and what kind of mobile devices they are using. So they answered us. They wanted to use mobile phones, PDAs, and laptops with different kind of network connections, like wireless connections, mobile connections. Secret switched or GPRS or even 3G. In the context of 3G, we can imagine the more bandwidth, for example, and we refined several use cases. How they wanted to use. In which way they wanted to use their mobile devices. So first of all, they wanted to steer the applications and jobs running somewhere in the grid, because grid by its nature is a distributed structure. So they wanted to have a possibility to steer these jobs running on the grid, for example, to stop, to postpone, to the next feature they wanted to have is to be notified about some events. For example, when the jobs is running somewhere, when the jobs will finish, they wanted to get some notification message. Notification, it means that mobile user doesn't care about the kind of the message. It would be a SMS, email, or even they at the beginning they mentioned about some fax messages even, but we postponed it to fax. Actually, we didn't develop some feature concerning fax messages. The next point, visualization for mobile users, because grid visualization prepared by grid applications, by its nature is there are huge pictures, huge files. So users they wanted to have possibility to see this large visualization of their mobile device. And the last one, offline working practices, for example, to define some job description and afterwards to start this job on the basis of this prepared description. These are the main features. I will not go into details, so maybe let's go directly to the main architecture. Our approach was to adopt grid gateway-oriented architecture. Here you have a gateway which is just which calls the grid services in the name of mobile device. The mobile device on the mobile device we are running Java Maker Edition client. We decided to use Java Maker Edition technology to meet the requirements. Write once, run everywhere. So our mobile client is running on mobile phone, the same mobile applications running on mobile phone, on PDA, or even laptop. So we have a mobile application, gateway, and grid services. The gateway grabs automatically the profile of a mobile device. The screen size, color depth, the class of device, and so on. And on the bottom we have grid services. As I mentioned you, the client is a Java Maker Edition application. the gateway is a mobile command center. We call it, this is our name, we call it mobile command center. This is a portlet of GridSphere, running on the basis of GridSphere portlet framework. And now you can see a general assumption of the visualization service for mobile device. The service is working in two modes. I mean, you can display the images, or you can display sequences of the images. Oh, okay. So, job steering. User is able to run jobs on the basis prepared on the mobile device. I mean, user can run the job, prepare the description of the mobile device, and afterwards he or she can run the job on the grid. And some pictures. I mentioned before that the same application without recompiling is running on different classes of devices. These are mobile phones, smartphones, iPad, and PC laptops. Here you can see, for example, this is a notification message which contains some URLs pointing to the visualization images. Here you can see the two black holes. They are coming to the collision, and you can see the sequence of the sequence of images. And here user is able to zoom into the bigger visualization. Okay, so the summary of our, as I mentioned before, the grid lab is finished already, but we didn't freeze the development. We are working on new classes of new scenarios for our mobile client, mobile services. For example, in weather forecast, you can imagine that, for example, when the simulation is running, simulation concerning the hurricane, for example, is running on the grid. And for example, the scientists they wanted to be notified by SMS the results of the simulation. I mean, the exact point of where the hurricane will hit the coast or something like that. Of course, we are still in the touch. I mean, with working on the Java Micro Edition technology. There are some different the next versions of this platform. Let's say there are still going works on efforts on for example, web services and security enhancements, and of course mobile devices are getting more powerful day by day. So maybe this is the next possibility to extend our mobile client. Okay, thank you very much.
So the floor is open for questions or comments. The two presentations. Yeah, one down here. Wait for the mic, sorry.
Question to the first part. You mentioned that you do the accounting concerning the flops, teraflops used. Did you also think about main memory or disk space used?
You know, the way it's working right now is that only teraflops are taken into account, because I described the way the HPC centers already provide these features for users, because the transnational access program is already running. What we want to do to make it on the global level for more than one center. But okay, so the concerning memory and for example disk space and so on, I think only you can set quotas on disk space, but not account and charge it.
I think the main memory is very. I don't know the English word. If you have great main memory, huge amount of main memory, it's very interesting to run a job on your supercomputer system, except it has not these teraflops.
Yeah, maybe you can then set the cost of one allocation unit very high, maybe, for such a machine.
Thank you. Are there any other questions or comments? Okay, if not, let's thank the speakers again. And let me introduce the third speaker, which is Radek Trivania. I don't know if the pronunciation is correct. He works at the Potsdam Supercomputing Center as a network application engineer, and it is involved in network measurements, transport protocol enhancements, and fast network and bandwidth on demand. He will talk about ClusterX, National IPv6 Computing Facility in Poland. Please.
Okay, so I'll be presenting the Polish national project, the ClusterX, which is the first grid in Polish distributed over the Polish territory. Going through the agenda, I will say what is exactly the ClusterX project. Then I will say a few words about the Pioneer network, which is the communication background. Then the network architecture that we create in the ClusterX project. Network as a resource, which is an application that provides the information to the other system that they can see the network as a resource actually. And at the end, I will say a few words about the feature of dynamic resource attachment to the ClusterX. So what is a ClusterX exactly? In the 2003, the 12 major Polish computing centers decided to join the effort to build the first Polish grid environment, which consists of the computing cluster distributed in 12 Polish cities actually. There were 4 primary objectives to build the system. The first one is straightforward and rather obvious, to build a productive and efficient grid environment. The second one is the security, because the security is the marginal thing in the grid environments, which is of course changing because the network is evolving. But in the ClusterX project, we want to also focus on that issue. Then we have to migrate from the IPv4 protocol to the new version of the routing protocol, which is IPv6 version. And the last thing is the scalability of the system. We want to have our resources, the possibility to add the resources dynamically and to remove them, to attach them temporally or permanently. The computing nodes in the ClusterX are based on the Intel processors for 64 bits, but they can also cooperate with the older version of the processors, and 32 bits are also possible as a temporary clusters. The number of 800 of those processors produce the computing power at the level of 4.4 teraflops, which make the ClusterX comparable with other installations around the world. We like to use an open source, whatever is possible within the ClusterX. So we decided to use Linux as an operating system. And we choose a Debian distribution as the base distribution for all installation computing nodes, management nodes, etc. The communication in ClusterX is based on the Pioneer network, which is a layer 2 network Ethernet. And over that, we have a IPv6 routing protocol. Probably most of you knows what the Pioneer is, but anyway, I will say a few words about it. It's a fiber-based network that interconnects the 21 research centers around the Polish territory, which over 3,500 kilometers of fibers. And DWDM technology provides a throughput at the level of 10 gigabit per second, which will be improved with more lambda channels up to 20, and then maybe 40 gigabit per second. By now, it's planned to have over 5,000 kilometers of fiber. This is the state of the Pioneer network at the end of this year. For now, we do not have 2 lambdas, but we are planning, and we are actually right now building the second lambda channels in the most congested links when the bandwidth utilization is high. The Pioneer network is, of course, connected to other research networks abroad. It's a GEANT network, CESNet, and to our eastern and western neighbors. For more information about the Pioneer, you can visit our website or ask in a box just in the main entry. Backing to the Cluster X, I would like to present the network architecture that we, after a lot of discussion, create in this project, which looks like this. That's a compromise between application and tools people, the security guys, and the network engineers. And we settled an agreement finally after a very, very long discussions. So from the backbone Pioneer network, we have a 1 gigabit per second link. It's a VLAN, so the traffic is separated from other backbone traffic. And the 1 gigabit is put into the local cluster switch. Before the traffic reaches the computing nodes and the access nodes, it is filtered with a router with firewall functionality. This router introduced the layer 3 to the grid environment, and that was the point of the problem between the application people and security people. This element introduced security in the form of the firewall and packet filtering, provides a layer 3 quality of service when we can prefer some streams with special marks in the IP packets, and provides an isolation of the clusters. So each cluster has its own subnetwork, and they have to communicate through the router. So taking control of one of the clusters doesn't mean that you have control over all other clusters, which can take place when we do not have a router and all clusters are in one subnetwork. In a local installation, we got 2 VLANs. Each is 1 gigabit per second VLAN for communication purposes and NFS purposes, file transfer, etc. There is also a connection to the internet for the administration purposes. Only outgoing connection is allowed, except the dynamic cluster, but I will tell you something about later. And all communication here is provided with the IPv6 protocol. We are trying not to use IPv4 anywhere whenever it's possible. At the beginning of the grid, the network was treated as a simple link between the computers. When the distance is growing, there are rising some problems with the network. The latency is growing, there is a packet reordering and other issues that have an influence on the computations. Now the network is being seen as a resource in a grid environment. We create an application within a Cluster X project that provides the view of the network as a computing resources that can be consumed, and it's actually working. The feature of the application was to have a view on the network, know its status in the moment, to know what is wrong, where is wrong, to find the problems, etc. We have the monitoring issues, the measurement issues. We know how to gather the statistic. We keep the statistic, which helps us to find the bottlenecks, network problems, etc. We also introduced the layer 3 quality of service to the management. It's performed statically because the routers are under control of the local installations, so we try to avoid a security problem here. We also want to minimize the administration influence on the system to not to give him too much work. So the management sessions are created automatically as far as it's possible. And also the system is resistant to failure, and in any case, he can recover his state after a failure automatically. This is the monitoring and measurement architecture in the Cluster X project. And the SNMP monitoring is performed only on the core switches in the Pioneer network because the local switches are under administration of the local infrastructure, local administrators. So we could find a problem with the community keys and then their access to those switches, so we decided to skip it and use only the core switches. So all information I get only from them, and actually it's enough for us. The active measurements are done in 2 ways, on 2 levels. The first level is the backbone level. There is a backbone measurement edges installed on access nodes and data storage elements. And we have the measurement in the Pioneer network there. Those edges works under the control of centralized manager, and all reports are directed to him. Under this level, we got the local cluster agents, which performs the measurements in the local clusters. Those measurements are averaged and sent to the backbone agent, and then forward to the manager. The measurement results are also stored in a database to have a statistical view of a longer period, because the manager keeps only the result for a limited time. Of course, all measurements are performed in IPv6. This is the architecture of our application. On the very top, there are external entities, which is from the left side, the database, when we keep the results. The external client, which is, for example, a task broker that uses our system to get the network parameters. The graphical user interface, when we can configure our system and manage it. And the last thing is a backup manager, which is actually a regular manager, but in a suspension state, waiting for failures. The system manager, the middle part of that is our core of the system. It's a Java written application. On the top, we have web service interfaces to communicate with external entities. The system logic is nothing more than a decision system, decision module, who forward the events to the proper modules, who decide whether to put results to database, whether to send some information to other modules, etc., etc. The measurement agent manager is the entity to manage the measurement sessions, the agents. This is the place where the agent register. And device manager contains the network topology as a devices, and have an access to those devices with the SNMP and ICMP echo request messages. On the very bottom, there are measurement agents, which are C applications. The communication between measurement agents manager and the agents are secured with this SSL protocol with some certificates, and this is our own protocol. The measurement protocol was based at the beginning on the O1 protocol, one-way active measurement protocol. But we encountered a problem with the synchronization between the nodes. We could not afford to have a GPS unit in all cluster locations. So the only thing we could do was synchronization via the NTP protocol. The precision of that was about 1 or 2 milliseconds, which was not enough. So we decided to use round-trip time measurements. The second problem was that some message that we would like to using was too long, and moreover the length was not constant. So it depends on the software configuration, hardware configuration, etc. So from this point, we decide not to use OWASP anymore, and we provide our own packets because we need not fixed length. The messages are still similar to OWASP messages, but the protocol are not compatible anymore. Of course, the protocol supports both versions on IP protocol. The cluster we use IPv6, but there is no problem to use IPv4. The traffic pattern message allows us to specify very sophisticated traffic patterns for the measuring. It defines at the level of each packet the pauses between packets, and the measurements are oriented in bars, which are repeatable each time it's necessary. The 5 network metrics that we measure are very common. They are well known by the network engineers, as well as they are not new for the grid people, so they know what to do with them. The monitoring, as I said before, only the core switches are monitored via the SNMP protocol. We get 3 things from them. The first is the network interface status, whether it's up or down, it's forwarding packets or not. The second thing is how much bandwidth do we have on this interface. So if the network is reconfigured and the bandwidth, available bandwidth is changed from, for example, 10 gigabits to 20 gigabits per second, the network management system should discover this automatically. And the last thing is link utilization, so we know how many bandwidth we are using now and how many bandwidth we still have to use. That's a very important information for the task broker to decide where the task should be placed on which clusters to have clear communications. To improve the security with the SNMP access, we are using the mechanism introduced in the SNMP version 2, which is called views. We have only read access to those MIB subtrees that administration allow us to see. It's okay for us, we don't want to change anything, and we have access to things that we need to know. As I said before, our system is somehow redundant to resistant to failures. That's the regular wonking, when we have a couple of managers. Only one of them is active, the other one is waiting in a suspension. There is an exchange of the information between those managers. They all know about all the agents, sessions, and other things that is required to restore the state of the system. As well as the communication is working, everything is fine. When the manager fails, then all other managers that were in a suspended state discovered the problem and start the election of the new active manager. During this phase, the agents cannot send the results, the measurement results, to the manager, but the measurements are still performed. So we are not losing any information about the network status during the problem. When the new manager is elected, is working again, the agents can register to it, send the data that can be forwarded to the database. So we still have a full historical view of the network status. The selection of the manager is done with the Booley algorithm with a little modification for our needs. Okay. That is the graphical user interface. It's a Java applet. It's still under development. For now, it's look like this. You can see there a map of all clusters, all interconnections. You may find how the local infrastructure is built, how many nodes you can find there. You can easily get the network statistic between any 2 points on the map, see the SNMP monitoring values. If anything goes wrong, if we have a problem, the administrator will be informed about it through this interface, and the localization of the problem will be marked on the map. The last thing is the computing resources that can be attached dynamically to the Cluster X project. How do we do it? Oh, sorry. What for? The first thing. We like to have dynamic resources to increase the cluster computing power, no matter if it's permanently or temporarily. There are some clusters on the universities, that the laboratories, for example, which are not used during the night or on the holiday periods. We can attach them easily to the Cluster X projects, improving the computing power. In the same way, we can also extend the base infrastructure of the 12 clusters with new clusters that are treated the same as the other ones. We do it by attaching the dynamic resources through the internet to the firewall router. We can omit the internet and plug it directly to the router, which is far more safe. To attach the resources, we need to fulfill a group of requirements, like proper software installation. We need to have measurement agents, computing software. We need to have security issues like SSL certificates, etc., etc. The all communication is forwarded to the router and firewall, because we cannot fully trust the things that is connected temporarily. And the network management system should automatically discover the things that is connected, because the agent starts registering in the system. So in any case, if we just plug in the cluster, we will see it in the system automatically without any administration activity. So summarizing the Cluster X project, it's based on the Polish national network with a 1 gigabit channel. We introduced the IPv6 protocol in everywhere where it was possible. So we are adapting an application, computing application, management application, etc., etc. We are immune to failures as far as it's possible. We use a network as a grid resource, fully grid resource, and we also allow an attachment of the dynamic configuration changes in the cluster. Thank you for your attention. If you have any questions, please ask.
Thank you, Radek. Other questions or comments to the last presentation? Okay. If not, let's thank Radek and all the 3 speakers for the session. So the session is now closed, and the lunch